a little bit of AP chemistry for you. So what you're going to see right now is that there should be a Pear Deck join code for you. So while you're on your computer, if you go to joinpd.com, and it'll ask you for a code, and just type in the EHVER that you see on your screen. And then this, if you've never used Pear Deck before, Pear Deck is basically like a PowerPoint where whatever I'm seeing is whatever you're seeing. And then whatever you're seeing, you'll also get a chance to interact. So there's a couple places where I'll ask you to maybe circle an answer, or I'll ask you to put in an answer or select an answer from A, B, C, D, do a calculation, stuff like that. And then I can see everybody's answer. We could see where we are. So instead of just sitting there listening, which is, I know, not everybody's favorite thing, especially in the virtual world, this lets you just be able to interact with everybody on here a little bit more. Now, along the way, if you have questions, feel free to unmute your mic and ask that question, or feel free to go ahead and type in the chat box on Google Meet that, hey, I'd really like to talk, or I'd really have this question, that kind of thing. So with that said, 3 of y'all are connected. Let's see what that looks like when everybody gets there. Hopefully everybody's back to school is okay. I know at least in North Alabama, where I'm from, it's a little bit dicey in terms of weather, as the hurricane came up into Texas and New Orleans, or Louisiana, and kind of took a right-hand turn. So that's causing a little bit of havoc up North Alabama, but hopefully where you guys are is okay. And hopefully you're enjoying your Friday, knowing that a weekend is coming. I also realize that most of y'all would just give anything to be back in class, for those of you who are still going full virtual. I know I miss my students, and being in a classroom. I actually retired this past year, but there's nothing like being in a classroom with students. Teachers love it. No one is really enjoying this virtual world, except for the fact that you can pretty much wear PJs all day long and no one's going to give you trouble. So, all right, so I got 4 people connected. Everybody else want to get in, or is that all 4 of us? Teachers, you too can get in there. Feel free to put in your answers. Oh, yes, everybody. Teachers, students, some person that just happened in here who's just interested in some chemistry. You're correct. All right, I got 18 people in on the Google Meet and only 6 in on the Pear Deck. So come on, everybody, let's get in there. Just go to joinpd.com, and it'll ask you for a code, EHVER. Works on a phone, works on a laptop. There we go. We're up to 8. For those of you who missed it when I first said it, Pear Deck is just something like a PowerPoint or like a Google Slides, except you're going to get to interact. So you're going to be able to select answers and move things around and circle things so that everybody's voices can be heard in terms of, hey, this is what I think the answer is. So there's no judgment-free zone like Planet Fitness. But we just wanted to give y'all a chance not just to sit and listen. We wanted to give y'all the chance to kind of interact with what we're doing today.
Hey, Danny, I got a quick question.
What you got?
I've never used Pear Deck. So can you upload a pre-built PowerPoint and then add in the slides and the questions that you want people to participate with?
Yes. I'm doing it from inside of Google Slides, which is the only way I've ever done it. But you could totally upload a PowerPoint into Google Slides. And then there's a Pear Deck add-on that goes along with it. But basically, you're just adding in things like ask a question and things like that. And then and then when you choose to present it, you don't present it from within the Google slide. You don't say present there. You do it from within the Pear Deck add-on.
Okay, got it. Thanks.
Right. We'll see how it goes. I've done this for myself and me and my wife. This is the first time doing it for multiple people, so we'll see how it goes. All right. Well, let's go ahead and get rolling while we're doing. So just a little bit about me, just so you know. I taught for 27 years, biology and chemistry. I've been an AP reader for a very long time. I've taught AP teachers how to teach AP. And during the summer, I spend an awful lot of my time on AP. So all that means is I know a lot about AP. And what's the goal here? The goal is at the end of this hour, do you feel a little bit better than when we started at 2? So at 3 o'clock, do you go, I think I got this a little bit better? And that's what we're going to be doing all year long, is just coming back to it and going, okay, yeah, I know what I'm doing. And if you don't know what you're doing, make a note of that. Ask your teacher, hey, can we go over that problem? Because this is being recorded. You can always come back to it later. So let's go ahead and get cranking. So somebody out there, remember the code is EHVER in case we get somebody that can't quite join. Right. So unit 1 is pretty simple in terms of it's largely stuff that you have seen in chemistry when you took it last year, and then maybe this first week of chemistry that you've kind of started back. So it's about that concept of the mole and what is a mole and how do you do stuff, empirical and molecular formulas, percent composition, and then we'll just touch on electron configurations. The plan is that with electron configurations, we want to just tease it a little bit, remind you about electron configurations, and then next week, same time, I'm going to want y'all to just go crazy and then start applying this information. So on the AP exam, there are a lot of questions that I call low-hanging fruit. There are questions from Chemistry 1. So what is a mole? Can you find the number of moles? Can you go grams to moles? Things like that. What is the empirical formula? There's lots and lots of really hard stuff on the AP exam. This that we're doing today is one of the easy things. So keep track of what are you good at? Keep track of what do you need work on? And then we'll just keep getting better every week until May when the AP exam is. All right, so what is a mole? What is a mole to you? So on your screen, there should be a thing where you can go down and choose an option. So down at the bottom, it should say, answer this question. So if you click on the answer this question, it should give you a couple choices. And then you can just click that choice, whatever you think that choice is. All right, so here's what I see. Out of 11 of y'all that are signed on, I'm seeing that 4 of y'all think that it's 6.022 times 10 to the 23rd of something. Good answer, great answer, you got it right. And 7 of you think that it can be used to find grams of elements or compounds. And you were right as well, because what we know is that the mole is something that's multidimensional. We could use it for all kinds of stuff, right? So we can use Avogadro's number to do things, right? So Avogadro's number is that 6.022 times 10 to the 23rd. Nothing you need to memorize. It is actually on that formula sheet that you guys have. So a mole of something would be 6.022 times 10 to the 23rd of something. You can also use the mole to find molar mass, right? So using molar mass, we can go from grams to moles. And the molar mass is just what is the number of grams in 1 mole of that substance. So you would go over to the periodic table and you would look up the mass on the periodic table. So hoping that you have a periodic table today. If you don't have a periodic table, you may want to open up a new tab or a new browser window and go ahead and find a periodic table because you'll need one today. But when I look at it, I look at something like, let's say, carbon. Carbon has a molar mass of 12.01 grams. That means if you had 6.022 times 10 to the 23rd, a huge number of carbon atoms, that many atoms would weigh 12.01 grams. We can also use the ideal gas law. Now, some of y'all may have had chemistry last year, and because of COVID, things got hosed up. Maybe you never got to gas laws. But there is a gas law equation called PV equals nRT, the ideal gas law equation, where P is pressure, V is volume, R is a constant, kind of like pi is a constant. Temperature, T, that's easy. And then N is the number of moles. So if we have everything else, pressure and volume and temperature, we can actually solve for the number of moles using the ideal gas law equation. We can also use molarity for solutions. Again, something you may or may not have seen if you took chemistry last year, but molarity is for solutions. So if you made up a salt solution or you made up an acid solution, we can't weigh it because it's got a bunch of water in it. So what do? We just categorize it as the number of moles divided by the number of liters, and we call that molarity. So if you have a 1 liter solution and we call it 1 molar, then that means that there's 1 mole of that chemical dissolved in that 1 liter of solution. The other way that you'll find the mole, not that we're going to do it very much today, but the other way you can use the mole is you can use the coefficients in a balanced equation. So if you have a balanced equation and you have the numbers out in front that you do stuff with, that gives you what we call the mole ratio. So if you have 2 moles of one thing, that it might take 3 moles of the other thing in order to get it to react. And I think of it like I think of Oreo cookies because I love me some Oreo cookies. So you take 2 crispy chocolate wafers and you mix it with 1 creamy white middle. So if I had 2 moles of crispy chocolate wafers, I would need 1 mole of creamy white middles in order to make Oreos. So you can also get at the number of moles by using those coefficients. So let's drag out your periodic table. Hopefully you have a calculator, but if you have 120 grams of calcium, how many moles of calcium do you have? So down there at the bottom, again, on your screen, you should have a thing that says enter a number. For those of you that are maybe still not on the Pear Deck thing, you would have to go to joinpd.com, and then you would just type in the code EHVER. So we want everybody in, and teachers, students, everybody. I don't see who answered what. All I do is see how many people answered what. So go ahead and take your time. This is something you all did probably in chemistry. So try going from 120 grams of calcium to moles of calcium. Keep them coming. Y'all are doing great. That's fine. We're in no great big hurry. All right, so 9 out of 13 so far, but let's see if we can get those, the other people. And if you're not sure, just type any number. Doesn't really matter. All right, so let's give y'all 10 more seconds and see if we can finish up in the next 10 seconds. All right, so for the most part, y'all did pretty well. We had some really big answers I wasn't quite expecting, but that's okay. So how many moles of calcium do you have? Well, let's look on the periodic table. So go find calcium on the periodic table and look for its mass. What is the mass number of calcium on the periodic table? And what you should notice is that it's somewhere close to 40. So the element symbol is Ca, and the mass of 1 mole of it should be about 40 grams. So if 1 mole weighs 40 grams, then how many moles would be 120 grams? And that correct answer should have been 3, right? So the math would look like this: 120 grams times 1 mole over 40 grams. And then 120 divided by 40 would give you 3. So you're looking for about 3 moles. Oftentimes on the AP exam, 3 moles, not 3 moles, sorry. Oftentimes on the AP exam, just finding the number of moles earns you a point on a free response question. It's a good skill to have. All right. So let's try this one again. This gives you the chance to actually type in the answer, but you spent all your time counting out atoms. So how many moles of iron did you count out if you counted out 3.01 times 10 to the 22nd atoms? Now, look on your reference sheet if you need to. And if you don't have that handy, I'll just remind you that 1 mole is Avogadro's number, which is 6.02 times 10 to the 23rd. So if 1 mole is 6.02 times 10 to the 23rd, how many moles of iron did you count out? And again, you ought to be able to click on that answer this question, and then you can come up with an answer and go ahead and type in what you think the answer is. And just so you know, it's okay to be wrong. Again, I can't tell who's doing what. Mr. Matt Dean or Mr. Ryan Richards, they both could be messing with me and typing in the number 500. I would never know. All I can see is these are all the possible answers people are putting in. Not that I want y'all to mess with me, you know what I'm saying? Keep the answers coming. Get out your calculator. That's fine. Remember, 1 mole is 6.02 times 10 to the 23rd, and you're given 3.01 times 10 to the 22nd. All right, so that's about half of y'all in. The rest of y'all who are still working, take a stab at it. It's just dimensional analysis. Start with the number you're given and use the fact that 1 mole is 6.022 or 6.02 times 10 to the 23rd atoms. All right, those of you who are still working, keep working. I'm going to give y'all like maybe 15 or 20 seconds to go ahead and figure out what an answer is. And you can just type in that number and we'll just see what everybody thinks. All right, so that's actually pretty good. Y'all stayed in a good range. No one got like 50 kajillion or anything like that. That was my concern. And the correct answer there, some of y'all got very close. You just need some practice with exponents. So the correct answer there was actually not 0.5, which several of y'all said. It was 0.05, because 3.01 times 10 to the 22nd divided by 6.02 times 10 to the 23rd is 0.5 times 10 to the negative 1. So you got to move that one more place. So that would have been 0.05. So what we know is you need to be able to go from moles to grams. That's a skill you need. And you need to be able to go from grams to moles, back and forth. And also be able to go from moles to atoms is also a skill that you need to make sure you're practicing all along AP chemistry, because this is something that you'll use over and over and over again. All right. Now, you guys probably did this in chemistry. This is a very easy thing to do. Percent composition is just a way of analyzing a sample. So you may find a moon rock, you may find something on the surface of Mars, or you may just find something in your bedroom and you just wonder, what in the world is this? Well, one of the ways to figure out what that is to analyze it. So break it down to its individual elements and figure out what percent of the whole sample is that element. So they'll do that analysis and they'll come back and say it's this much this and this much that. And from that, then you can kind of work towards figuring out what it is. You can also go from a chemical formula to a percent composition. So if you look over on that right-hand side, they give you the formula KMNO4. To figure out its molar mass of 150 grams, you would have to go over to your periodic table. You would look up the mass of potassium, that would be 39.1. The mass of manganese, that would be 54.9. And the mass of 4 oxygens, and that would total up to be 64. When you add it all together, you get 158. Then to figure out the percent composition, you would take the part, that is potassium, 39.1, divide it by the whole. Because remember, percents are always the part divided by the whole. So you would do that for K, and you would do that for Mn, and you would do that for O. Do that for each element. And you'll notice that all those percentages should add up to 100%. So just as a double check, you can kind of do that math. 24 and 34 is 58-ish, and another 40 is 98-ish. So yes, our answers are adding up to really close to 100. So far, so good. So what can you do with percent composition? Why is this a useful thing? So let's say you found a percent composition. You can actually try to figure out what something is. So I've given you a scale down here at the bottom. And if you know the formula CO2, what percent by mass is the carbon in the compound? So I want you to figure that out. So real quick, remember, add up what the whole thing weighs for its molar mass, take the part of each one and divide it by the whole. So instead of 3 elements, I'm only giving you 2. So go ahead, take a moment and calculate what percent by mass is carbon in carbon dioxide. And what it'll ask you to do when you answer the question is you're actually sliding a symbol back and forth to where you think it fits. Go ahead, give it a try. Five of y'all so far, so good. Let's see if the rest of y'all can get in. All right, that's half of y'all. That's great. Let's see if the other half can get in too. Where do you think it is? What percent is carbon in the carbon dioxide? 9 of y'all so far. That's great. Keep it coming. All right, so far so good. So quick question for all of y'all out there. Are y'all seeing the responses appear and disappear at all? Is anybody seeing like the responses show up and then disappear? Mr. Poe, do you see the responses show up and disappear, or do you just see the same thing every time? Okay. So when I'm looking at the responses, you guys are seeing the responses. So I'm giving away the answer is what I'm saying. Okay, thank you. All right, good. So Matt, we can show them as long as you're showing that same tab. Okay, that's good. True that. Okay, thank you. Thank you, Alyssa. All right, so I'm going to stop sharing my app so I don't give away the answer. How about that? Okay, so because I'm getting used to this too. So, all right. Now, how did you do that? Well, you took the amount of carbon, 12, and you divided it by the total 44. So 12 divided by 44, I got like 0.27, and we know that's like 27%. So far so good. That's great. All right. I just had that thought right in the middle. I was like, I wonder if they're seeing the answers. So, all right. So let's keep going. Can you find the percent? And oftentimes you'll see that on the AP exam as well. That's low-hanging fruit, stuff you got to get. You can also take that percentage and you can do what's called a empirical formula. So the steps of an empirical formula are change the percent to mass, change the mass to moles by using the molar mass. You divide all of them by the smallest, and then you make it whole. So here's an example of one I did, and here in a minute, we're going to have y'all do one as well. So it's 52.14% of carbon. So the first step was change percent to grams. So I just literally changed the percent to grams. The second step was change grams to moles. I'm dividing by the molar mass. And then the third step was to divide by least. So look at all the numbers of moles, pick the smallest number, and then divide each number of moles by the smallest number, and you'll get a simple ratio. So instead of 4.35 and 13.12 and 2.17, instead, when you divide by the least number, so divide all the number of moles by whichever number is smallest, you'll get a ratio of 2 to 6 to 1. And we get 2, 6, and 1 for our empirical formula. So sometimes you have to worry about what if it's 1.5 and 1. So when you make it whole, if you had 1.5, 6, and 1, you may need to multiply everything by 2 because you can't have 1.5 atoms. So when it says make it whole, it really just means multiply by something. Right? So let's go ahead and see if y'all can do a sample I found for you to do. So the compound is 43% phosphorus and 56% oxygen. So there's your percent and all your steps. And then you have a chance to write your response. So now that I'm not showing you answers anymore, go ahead and write what you think the answer is. So do the math. It'll take you a minute. That's okay. I got 2 of y'all in. That's great. Keep trying it. Just follow the steps that are there. Work with your calculator. Find the answer and type it in. Even if it's wrong, the goal is to be better today at the 3 o'clock than we were when we started at 2. All right, we got 6 answers in so far. Y'all are doing great. Just keep it coming. All right, so let's give y'all like another 20 seconds. And just keep in mind that if you can't see it on your computer screen or whatever, that may mean that you just have not joined the Pear Deck presentation. So you'd have to go to joinpd.com and you'd have to enter the code EHVER, and then you'll be seeing what we're seeing. Kate, I'll go ahead and jump in with the answer what you asked Matt. You as a teacher, you see all the responses. There's like a toggle button that says see responses, don't see responses. So as a teacher, yeah, you can see them. And I will say, Michael Poe, Mr. Poe, you do count, even though you're wearing that Auburn shirt, just because everyone counts. So I can't tell if it's an Auburn mask, but part of me says it must be. So, all right. So what I got was P205 when I found that answer. So I changed phosphorus from percent to grams, 43.7 grams, and I changed oxygen from 56.3% to 56.3 grams. I used the molar mass of phosphorus and the molar mass of oxygen to change each one to moles, and then divided both number of moles by whichever number is smaller. And then once I did that, I got a ratio of 1 phosphorus to every 2.5 oxygens. So it was P1, 2.5. I mean, O, 2.5. So I can't have a 1 to 2.5 ratio. So down here where it says make it whole, what that's saying is that you need to multiply both numbers by some whole number to get it to be a whole number. Sorry. So if it's 1 to 2.5, you need to multiply both things by 2, and then you get a P2O5 ratio. And a lot of y'all got it right, and that is great. Like P2O5, and the empirical formula is the simplest whole number 10 for an empirical formula, because you can actually simplify those numbers. So for a molecular formula, you're often given an empirical formula and asked to find a molecular formula. So it tells you in this problem that the empirical formula here is CH2O. And it tells you that whatever that molecule is has a molar mass of 360. So it becomes what I always tell my kids, a Gazinta problem. Yes, you heard me say Gazinta. So 360 is the molar mass, and the empirical formula adds up to 30. So how many times does 30 Gazinta 360? So we take the molar mass and you divide it by the molar mass of the empirical formula. So 360 divided by 30 is 12. So that means we take our empirical formula, CH2O, and we multiply that by 12. So it'd be C1 becomes C12, H2 becomes H24, and O1 becomes O12. So let's see how this thing works, and let's see if you can do this problem. See if you can come up with what is the molecular formula of this compound. And for this one, you get to draw on the slide. So for this one, you can circle or underline where you think the answer is. So you can click on that, answer the question, and then you can use your finger if you're on a phone or a pad of some kind, or you can use the mouse to actually squiggle or draw a line. Matt, my question is, I'm sitting here doing this because I haven't given this thought, is if we're recording this, are they seeing the Pear Deck? Unless I share my screen? I just had that thought.
Yeah, they are not. So it might be a good idea for you to go ahead and share, Danny.
Okay.
I didn't think about that either.
That's okay. I was just like, wait a minute. All they're seeing are a bunch of people's faces and icons. So
yeah, right. It's probably a good idea for you to go ahead and share.
Yeah.
And then just don't put up the student responses until the end.
Right. I'm with you. I should put up a fake set.
Yeah, there you
go. That's right.
Lead them the wrong way.
That's right. So now you can see. Students, you know how teachers always have it figured out with technology, and we always know exactly what we're doing. That's just like now. So
exactly.
Y'all know this whole technology, and some of y'all going back virtual, it's just been a hot mess. So we'll get better. Trust me. My goal is to be better next week than I was this week. So.
Danny, speaking of next week, will the same time work for you next week?
2 o'clock next Friday is awesome, unless everybody else needs to make a change. You just got to let me know one way or the other.
We'll schedule it up, and we'll go with two next week. Same time.
Okay. All right. Whatever works for Mr. Poe is fine.
We'll try to keep it consistent. Keep Mike happy.
That's right. That's right. All right. So far we've got 7 answers, and I will tell you God's honest truth or the higher power of your choice, whatever makes you happier. I missed this question the very first time because this is actually from an AP exam. I missed this question the first time I answered it. So if y'all get this question right, you are better than me. You are smarter than an AP teacher. So we're going to see how this works. All right, so let's give y'all another 10 or 15 questions. I mean, 10 or 15 questions. 10 or 15 seconds. How about that? And go ahead and come up with an answer. And remember, your responses you're just drawing on the screen. And since I don't have the paid fancy version, I can't see who did what. So all right, so let's see what y'all put for answers. Look at that. Look at that. Everybody picked C2H6. So let's see if you're right or not. So it's equimolar constant amounts of carbon dioxide and water. Which of the following could be the molecular formula of the compound? Well, if you have equimolar, that means equal number of moles. So you would have 1 mole of carbon dioxide and 1 mole of water. So if you have 1 mole of carbon dioxide, that would be the same thing as having 1 mole of carbon. So don't worry about the dioxide part. So you produced 1 mole of carbon and you produced 1 mole of water. So if you produce 1 mole of water, how many moles of hydrogen is that? Well, 1 mole of water, remember water is H2O, so 1 mole of water is actually 2 moles of hydrogen. So in the reading of this, what they're asking you to see is that you get 1 mole of carbon, so C1, and you get 2 moles of hydrogen, H2. So which one of those answer choices matches up with 1 carbon and twice as much water? This one down here. So letter C is actually the answer you're looking for. For every 1 carbon, there's twice as many hydrogens. So this would be an example of finding the molecular formula using the clues provided. All right. So let's keep going. This is just a reminder about electron configurations. Now, some of y'all may have just started schools and you haven't really quite gotten into electron configurations, but I'm guessing all of y'all did it in chemistry class. So if you did it in chemistry class, this is something that you might be shaky on, and that's totally okay, all right? So just as a brief reminder, you've got rows on the periodic table. Rows on the periodic table correspond to energy levels. So look at the periodic table. You got hydrogen and helium in that first row. That would be the first energy level. And then you've got the second energy level, and then the third and the fourth and the fifth and so on, right? So those are the levels of the periodic table, and those correspond to energy levels. The first energy level is the closest to the nucleus. The second one is a little bit farther out. Third one's a little bit farther out, and so on. Now, for every energy level, you can have sublevels. So, for instance, there's S, P, D, and F. That means that there's a 1s, because in the first energy level, there's an S sublevel, and there's a 3s, and a 2s, and a 4s. And that's where we put those electrons are in those sublevels. So one energy level can have multiple sublevels. So for example, the first energy level only has S. But if you go down to the fourth energy level has all 4 sublevels. Now those sublevels hold different amounts of electrons. So we'll do that here in a second. Within those sublevels, you find orbitals. So for example, the 3p holds 6 electrons. That means that to hold 6 electrons, you need 3 orbitals, because each orbital can hold 2 electrons. So one spins up and one spins down. So hopefully this is kind of coming back to your brain and you're going, oh yeah, I kind of remember that. So when we talk about an electron, first thing we do is say, oh, it's in the 4th energy level. And then we say it's in the p sublevel. And then we say it's in the 2nd orbital in the 4p sublevel. And then we say, oh, by the way, it's the electron that spins up. By doing that, we can identify with those 4 pieces of information, we can identify any electron anywhere in an atom. And then we want to use that information next week. So this is a periodic table that you're not going to see on your periodic table, but it just reminds you, this left-hand part of the periodic table is the 1s, 2s, 3s. So this is the S section. And notice that the S section is 2 blocks wide. That's because the S section has 1 orbital and can hold 2 electrons. So just remember, S holds 2 electrons. The P sublevel is over here in this section over here of the periodic table. And it is exactly 1, 2, 3, 4, 5, 6 elements wide. So this is the P section because P holds 6 electrons. So there's 3 orbitals, and each orbital has 2. So that means the total P section holds 6 electrons. Remember, the 1s are the closest, and then the 2, the second energy level, is the next closest, is farther away, the third one is farther away, and so on. Now, the weirdness, and you may remember this from chemistry, is the D's are always 1 behind, and the F's are always 2 behind. So you don't need a diagram or anything to help you do electron configurations, and we'll go ahead and go over them again next week to help remind you. But we can just go through and say it's 1s, there's 2 blocks, so it's 1s2, and then 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. And so you can lay out all the electrons an atom has and kind of go in order. So this just kind of reminds you how the electron configurations go. So let's see if we can actually do one. So oxygen has 8 electrons, and what is the electron configuration? So it's 1s2, that's 2 of the electrons. And then after the 2s, after the 1s comes the 2s. So we put 2s and it holds 2, so that's a total of 4 electrons. And then you could put 6 in that 2p. So let me remind you, 2 in the 1s, 2 in the 2s. 2p will hold 6. However, we can't hold 6 because notice I made a mistake down here. 2 plus 2 plus 6 is 10, and oxygen only has 8 electrons. So I can't spend 10 electrons. I'm not a congressperson, right? So 2 plus 2 is 4. That means this 2p6 right here should be 2p4. So you fill them up. You start at 1s, and then you go to 2s, and then you go to 2p. And if we fill up the 2p, then we would go ahead and continue on to the 3s, etc., etc. So let's see. Let's give y'all a chance to do one and see if you can write the electron configuration for aluminum. Do not worry about doing superscripts and subscripts and that kind of thing. Just what do you think the electron configuration for aluminum is? And if you have trouble finding it on the periodic table, it's element number 13. So Matt, I think what I'm going to do next week is I'm actually going to open up the Pear Deck in a separate browser window. So I'll have one open as a teacher and one open as a student, and I will just share the student screen, and that will solve both problems.
Yeah, that works. I know some people use two devices, so they have one device open.
Right.
So they can look at the responses, and the other device is the one they're sharing. So
right.
Whatever works for you.
Okay. I didn't even give thought to that. So. All right, we got 8 of 21 responses. So we'll give y'all just a minute because we're coming in on 5 minutes left, and I want to be respectful of y'all's time. And again, this is just kind of a review, so if you don't remember it, that's okay. We'll touch on it next time as well. But you may want to ask your teacher, hey, can you go over that one more time? Or Mike, Mr. Poe, you may want to ask your students if they can go over it with you so you can remember it too. So. All right, so let's see what your responses are. So if we look at everybody's response, oh, look at people getting all excited and fancy with their little caret symbols right there. Everything looks great. So if we want to double check, I know it's got a certain number of electrons. So it's got 13 electrons. So 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, and one more is 13. So this is the correct electron configuration. Now, just as to remind y'all, how do we use this and what is this helpful in? Y'all may remember the word valence, and the valence shell is the outermost layer of electrons. So if you're asking how many valence electrons does aluminum have, we know it has 3 because the outermost occupied energy level, so the farthest energy level out that has electrons in it, is the 3rd energy level, and there's 2 in the S and 1 in the P. That means aluminum has 3 valence electrons, and we will need that definitely next week. So that's just a reminder of what we do with this. All right, so I just want you to take a stab at this question. So this is another AP question. This has to do with moles. And if nothing else, if you can't figure out what the answer is, and you're going to choose A, B, C, or D, I want you to at least figure out what the answer ain't. Because half of the time on the AP exam, it's all about what ain't the answer. So just go ahead and take a stab at it. All right, so I got 4 answers in so far. All right, we're up to 6. That's great. All right, so let's go ahead and close it. Let's see what everybody said. So we had some B, and we had some C, and we had some D. So y'all were pretty even across the board. So no gas will be produced. No, everybody said that ain't it. If you look at the periodic table, one of the key things that we know about the periodic table is things that are in the same column up and down tend to react the same. So if you notice, Li and K are both in group number 1, that first column. So those are very reactive gases. So if lithium produced gas, then we think, yeah, so should K. Potassium should as well. So A is out. Some of y'all said equal quantities of gas, and some of y'all said more gas, and some said less. So y'all were kind of all over the place. So the correct answer here is actually B. And let's think about that for a minute. Why would that be true? Well, lithium has a molar mass of right around 7. That means 1 mole of it weighs 7 grams. Each lithium doesn't weigh very much because it has less protons and neutrons. K, on the other hand, if you look on the periodic table, has a molar mass of 39. So it's almost 7 times or 8 times heavier than lithium is. So what it's asking is, who has more moles of chemical? The more moles of chemical you have, the more gas you will produce. So if you were to try and do some math with this, what you would find is that there's less moles of K because every K weighs a lot. So since each K weighs a lot more than each lithium, it's kind of like saying, which is going to give you more things? A pound of little tiny grain of rice, which one will give you more things? A pound of grains of rice or a pound of bowling balls? Well, each rice weighs so much smaller, so much less. There's actually going to be more mold, more number of particles of the rice than the bowling balls. So the correct answer there is, since there's less moles of K, that there will be less moles of gas produced. So less will be produced than with the lithium. So with that said, I hope that gave you kind of a, yeah, welcome back to chemistry and AP chemistry. And hopefully that it reminded you a little bit more, hey, how am I supposed to do these problems? How does the mole work and stuff like that? And the most important thing that you can take home is, as you work these problems, I would love for you to talk to your teacher and say, hey, can we go over finding particles or atoms or something like that? Or, hey, can we work one of those empirical formula problems? And trust me, we gave your AP teachers tons and tons of those problems. So it's all about practice and getting better so that by the time we get to May, we can just kick the butt of the AP exam. So with that said, I'm done. I'm happy to stick around for a minute if you guys have questions. Otherwise, thank you so much for coming.